So we're going to have a look at mass spectroscopy again, and I'll just do a little recap on what we've done earlier in the year. So if you remember the way the mass spectroscopy works, there's several stages. So the first stage is at this point here. Hang on a minute. At this point here, why is it not working? At this point here, the sample is vaporized, and then either an electron is removed or a hydrogen ion is added, and of course that creates a positive charge. It is then accelerated, so this point here is a highly positively charged wall with a hole in that attracts the positive particles, and then we get acceleration all the way down here. And of course, remember, the speed at which it moves down there is proportional to the mass of the ion. So if it has a large mass, it moves slowly. If it has a high mass, it will move quickly. And the time it takes to get down that tube to the detector is proportional to the mass basically, but we call it mass charge of that ion. And then when it gets to the detector, it picks up an electron. The more electrons that are picked up, the greater the current that flows, which gives you something that is proportional to the abundance. Okay, so that's basically what happens. All right. Now, the reason we're coming back to it is let's just talk a little bit more. Remember, the key thing that we get from mass spectroscopy is this thing here, that MZ peak there, which is equal to the MR, which allows us, when we're doing our kind of carbon, hydrogen, and maybe oxygen empirical and molecular formulas, it allows us to convert it from an empirical formula to a molecular formula. Now, the mass spec that we've got here, there's a high resolution version of it, which basically means it will determine the masses of molecules to 4 decimal places. And you might be thinking, what the hell? Like, if these things are only made up of atoms, and atoms are only made up of protons and neutrons, how on earth can we have things that have units greater than 1? Okay. And it is a tricky one to kind of get your head around, and I'll just show you in this table here. So it was all a bit of a mess historically, because physics used a different atom to chemistry in order to say, right, this is the atom that we're going to kind of definitively say has a mass of, for example, physics I think used oxygen, which was 16. So ultimately we came to carbon, and carbon has arbitrarily been chosen as the one that has a mass of 12. Okay. Now, that doesn't mean that the proton and the neutron are equal in mass. And remember, the mass spectroscopy is only picking up either single atoms or single molecules, which means the isotopic abundance doesn't give you the kind of the fraction of a molecule. We're not working out the relative atomic mass, that average. What we're getting here is actual values of ions or molecules to 4 decimal places. And it comes down to the fact that the proton and the neutron are not equal in mass. Okay. Now, those of you that do physics will either already have, or if not will have, a greater understanding of this, but it comes down to the fact that basically protons and neutrons are made up of quarks, and they have directions, etc., etc. Because of the way they're made up, the proton and the neutron do have slightly different masses. And if another way to think of it, particularly for the physicists, is neutrons do or can decay in order to give you a proton and an electron. Okay, so if you think of one particle producing 2, they can't be exactly equal mass. Okay, so this high resolution mass spectrometer will allow you to work out molecules to 4 decimal places, which is absolutely crucial when we look at molecules that to kind of 1 decimal place or even 0 decimal places would have the same MR. And there's some examples here. So we've got C3H6O, C4H10, and C3H8N. All of these, if you work out their MRs on the periodic table, have an MR of 58. But of course, if you look at what they are made up from, so this one here is made up of 3 carbons, 6 hydrogens, so there's your hydrogens there, the actual mass to 4 decimal places, and 1 oxygen, which is that one there. Butane, C4H10, so this is, the 58 in this is made up of a different combination of only 4 carbons and 10 hydrogens. So to 4 decimal places, the mass of C4H10 will be slightly different from C3H6O. And again, if we look at the final one here, C3H8N, it has an MR of 58, but to 4 decimal places, it will be slightly different. So if we were to work them all out, we'd have 58.0406 for C3H6O. For C4H10, we'd have 58.0780. And for C3H8N, we'd have 58.0655. So not knowing which one of these 3 potentially you have, if you put in a high resolution mass spectrometer, it will give you the MZ or the MR basically to 4 decimal places, okay? Which in this molecule here, so you're told in the information that this molecule has an MZ of 58.0408, which means it must be C3H6O. So no difference essentially between the 2 types of mass spectroscopy machines. The only difference is that one is a lot more precise, which allows you to distinguish or determine molecules with similar MRs. Okay, there's again some questions on the link to Moodle, which is part of your homework for you to have a go at there. So again, that's a good point to stop before we do the last section.